Another method of finding volumes of solids of revolution is using something called shells. We did an exploration in class that should introduce this idea to you. But if you look on your notes, the page says 164 at the bottom. You should be able to see at the top there kind of what we're talking about. Now, on this page, we go through a little bit different method of coming up with the equation than we did with the exploration. Both are valid, both end up with the same thing. So you need to understand both. If you have a rectangle, now all of our others when we did discs and washers, our rectangles were perpendicular to our axis of revolution. With shells, it's parallel to the axis of revolution. So that's what makes it different. And we'll rotate it around, and we end up with this cylinder, but it's like a can. It's only the outside part. So that's a really rough sketch. The picture on your printout is better. But you can see that you've got this rectangle and you've rotated it around at the axis of revolution. And if you label the width of the rectangle W, and this, I would call it a length, we'll call it H, and then from the axis of revolution to the center of the rectangle, we'll call that P. You can look at this and figure out how to find your volume of this little shell. So if we have the shell, we've got, it's kind of like washers where you find the volume of the outside and then subtract off the inside. So the volume of the outside part, well, for a cylinder, which is what we've got pi r squared h is the volume of a cylinder, remember? So we have pi, and then we need to figure out what the radius is. Well, this outer radius, if you notice that this width is W here, and we're going P goes to the center, then this outer radius is P plus W over 2. If you don't quite see that, pause it and make sure you've got that. So we've got P plus W over 2 squared times H. Pi r squared H for the outside. Now for the inside, we've got pi, and again we've got an r, except this time we're going to this inside part. So it's the P, which goes to the middle, minus W over 2, because that length is W, so we subtract off half of it. And pi r squared H. And so what we're going to do is we're going to take this whole volume and we'll have pi H times P plus W over 2 squared minus P minus W over 2 squared. And if you FOIL that all out and combine your like terms and everything, simplify, which I'm sure that you know how to do, you get pi H times 2PW, which is actually what we had when we did the exploration. Remember, with our exploration, we said that the volume was 2 pi times the height of it times the radius out, and then our width was, we called that d. In this case, it would be dy because we're measuring along our width along the y-axis. Just remember that any of these have to be functions of y if we're using dy. So that's pretty brief, but that whole first page of your notes is kind of just a reiteration of the exploration. So just go make sure you understand that exploration and kind of go through that first page of your notes. Go ahead and pause it now and make sure you've got that whole first page down. All right, so on the second page of your notes at the top, there's a couple of formulas there, and it's giving you the volume if you have a horizontal axis of rotation and a vertical axis of rotation. Remember, with shells, you're parallel to the axis of rotation. You're going to have, most of the time, I just want to point out that most of the time your P of y, if we're revolving around the x-axis, then it's just y. Just like if we're revolving around the y-axis, then our p of x is just x. So that's where you have your function. The h function is where you have the actual function usually. So let's look at this example here. Let R be the region bounded by the graphs y equals x squared plus 4, y equals 8, and x equals 0. Set up and evaluate the integrals that gives the volume of solid generated by revolving R about the y-axis. So what we have is this parabola and this line here, and the line x equals 0, which is the y-axis. So the area we're looking at is this area here, and we're revolving it around the y-axis. So that means that we're going to go around this way, which will give us this volume here. Now, the first part says to use the disk method. I want you to pause it and go ahead and find the area using the disk method. Okay, so let's see what happens if we use shells instead. You noticed in the disk area, with the disks, you had to use a dy, but if you're going to do shells, we're actually going to do a dx, because remember, shells go parallel to the axis of rotation. I find it helpful with shells to draw myself a separate shell off to the side to label everything. Okay, our width is in the x direction, so we're going dx. Our height is from this part up top here down to the function. So this one here is 8 minus, and then our function, x squared plus 4. So if we simplify that, we have 4 minus x squared. And then our radius for our shell, our p-value in this case, is just x, because we're measuring from 0 out to some x value. So now we just have to figure out our volume. Well, the volume is the integral. We're going from 0 to, we need to see where this hits. This hits at the point 2, 8, so we're going from 0 to 2 of 2 pi r h, and then the width of the cylinders. So we'll pull out our constants and go ahead and distribute that in so that it's easier to deal with. And we get 2 pi times x squared over 2, 2x squared, 2x squared minus x to the 4th over 4, evaluated from 0 to 2, which gives you 2 pi times 2 squared is 4 times 2 is 8, minus 2 to the 4th is 16 divided by 4 is 4. And then plug the zeros in, you'll just get 0, so that doesn't help us, and we get 8 pi cubic units. And that's what you should have gotten when you got the disk method. But you see, with the shell method, it's useful because we could use the dx in this case instead of having to use dy. Now let's at least set up a couple of other ones. If you look on the back of that example at the top, we're looking at a region bounded between y equals 1 over x, y equals 0, x equals 1, and x equals 4. And if we take this and draw this in, we end up with, that's x equals 1, and this is x equals 4. We end up with something like this. This is our region. And the problem asks us to revolve it around the y-axis. So when we revolve it around the y-axis, we're going to end up with this region over here. It's going to go around. Now, you might say to yourself, well, I could do that with washers. Well, you could do that with washers, but then if you look, see, your radius, your outer radius up here hits the function, but when you get down here, you'd have to change to a different radius, outer radius. But if we use shells, we don't have that problem. Because if we use shells, then we're taking our width dx. The height is the same throughout. It's this function 1 over x. And the radius is x because we're rotating around the y-axis. So we're measuring out by x. And so we end up with actually a fairly simple integral. The volume is just the integral. We're going from 1 to 4, remember? The integral of 1 to 4 of 2 pi r h dx, which is the integral from 1 to 4 of 2 pi dx. So it's just 2 pi x from 1 to 4, which gives you 6 pi units cubed. So you see that if we had used the washers, we would have had to split it up into separate integrals, and we would have had to use y-bounds because we would have had to do it dy, and it would have been a little bit more complicated. But with shells, it's actually very easy. Let's do one last example, that next one there. If we have the function y equals x cubed plus x plus 1, and y equals 1 and x equals 1, and we're revolving around the line x equals 2, then what we have looks like this. We actually have this function goes up like this, and the line y equals 1, or excuse me, x equals 1, and the line y equals 1, so that we have this area here, and what we want to do is revolve it around this line x equals 2. Now the biggest thing when you revolve something around not one of the axes, it changes the radius. You have to pay attention to how you're handling the radius. So again, we could use washers, but if we use washers, we're going to be integrating with respect to y, which means we need this function in terms of y, and you can see that that would be a little bit complicated to deal with. So if we use shells, we don't have that problem, because with shells we're going to be able to integrate with respect to x, because when we use shells, we integrate, we go parallel to the axis of rotation. So now we have to look at our height. Our height is going to be from the top to the bottom. Remember, you always look at the original area to measure off your heights and your radii. So we are going from the top to the bottom. So our top is the function, and then the bottom part is this line y equals 1. So we just have x cubed plus x as our height. And then the radius, we're measuring, remember, you measure from the center out to the original area. So we're start at 2 and we're going out to the function. So, or out to the x value of whatever we're measuring. So our radius is 2 minus x. Okay, so you start at the x value, and then we're going, what x value do we hit next? Well, it's whatever x value is of the function. So our volume, then, we're integrating, well, this is at 0 and it goes to 1, so we're integrating from 0 to 1 of 2 pi r h dx, and you can integrate this all out and calculate it, and you get 29 pi over 15 units cubed. Make sure you actually take the time to integrate that out and check it. And yes, it really is important that you try to get exact values. I know you guys love to plug them in your calculator, get me a decimal approximation, but you really, really do need to be able to give exact values as well. So, what's the difference with shells? Shells, unlike washers and discs where your width is perpendicular, with a shell, your width, you're revolving parallel to the axis of revolution, which often makes it more useful than washers, especially. Washers and shells would be used in similar times, so you have to choose which one. And now that you've got all these methods, washers and shells and discs, you need to look at the problem and say and ask yourself, draw yourself a picture and say, what's the best method here, and don't let me choose it for you. Although I will say that generally speaking, every problem has a best method, and it should be the same for everybody. So read the section, and your assignment in class is going to be to do the rest of the problems in your notes packet. So you can get started on that if you feel comfortable with this. Make sure you've written down any questions you have so we can go over them in class.